Welcome, guys. We are going to get started on IS number 15, confidence intervals for means. So in our last lesson, we learned all about how confidence intervals work, and then we actually learned to construct confidence intervals for proportions. So it is time to move on to means. So here's the setting of our problem. It says Mrs. Bakula wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised, right? And I want my Oreos to be full of the cream they're supposed to have. So I selected a random sample of 30 cookies and found the weight of each cookie in grams. So I'm not going to give you the individual weights, but I am giving you the mean weight was X bar is equal to 11.1921 grams. Of course, that is our sample mean. With a standard deviation of S sub X or S are the same thing, equal to 0.0817. Then it says to make a 95% confidence interval, that confidence level will be important, to estimate, and this is also important, it tells us what our parameter is going to be, the true mean weight of an Oreo. Okay, so let's get started. For some reason, my numbering is really off and it starts at number 4. Whatever, I'm going to roll with it. So it says, what is the point estimate for the true mean? So just like with the point estimate for the true proportion being the sample proportion, the point estimate for the true mean is the sample mean. So we're going to write in here X bar is equal to, okay, it's 11.1921 grams. Okay, so that's our point estimate. That'll be the midpoint of our confidence interval and how we construct it. So let's see what other information we need. It says to identify the population, parameter, sample, and statistic. Okay, so the population. I'm trying to estimate the true mean weight of an Oreo. So I'm really thinking about all Oreos that are out there. So my population is all Oreos. Okay, and then the parameter to go along with that is, again, what I'm trying to estimate. So that's mu, the true mean weight, of Oreos, true mean weight of Oreos. Okay, so then the sample is what I told you that I took earlier. So, I should have underlined that, I guess. It was a random sample of 30 cookies. Of course, that's going to be important. But that tells us our sample, what we actually took. So I'm going to write down here that it is 30 randomly selected cookies. Remember that RS stands for randomly selected. And then my statistic is the sample mean. So again, X bar is equal to 11.1921 grams. Notice with proportions, we didn't have units because it was truly a proportion, which we could relate to a probability or a percentage. These are averages, so they have units of measurement, and we're going to continue to try to use them. Okay, so then it asks, was the sample a random sample? Guess what? That's going to be a condition for us, and it asks, why is that important? So let's go ahead and answer that question. Yes, it was a random sample because it told us in the problem that it was a random sample. So yes, and it is important. If you remember, we talked about this a little bit in the last notes. It's important that we have a random sample so that we can generalize our results to the whole population. So that's what I'm going to write. It's important so we can generalize to the whole population. Okay, so we've got a random sample, that's good. So then it says, what is the formula for calculating the standard deviation of the sampling distribution of X bar? That should call us back to think back to section 6.5. This is when we talked about that central limit theorem, and that was all about the sampling distribution of X bar. So it told us in that central limit theorem the mean and standard deviation we could expect. So that was that sigma sub X bar formula, right? And if you remember, the standard deviation for the sample means actually got smaller than the standard deviation for the entire population. So we took the standard deviation for the population and divided by the square root of n. Okay. where n, again, is the sample size. So we're going to move forward from that and think about what the condition that must be met to use this formula. Well, when we're talking about a sampling distribution, one of the things that we kind of skipped over in section 6-4 was that those samples are usually done without replacement. But that's okay as long as the sample is a small enough portion of the population that it doesn't really change the probabilities. So this is really similar to samples where we're calculating proportions. The 10% condition has to be met, right? This is kind of an expansion of that 5% guideline for cumbersome calculations. We're going to expand it to 10% for these confidence intervals. So basically that means that our sample size, which here was 30, must be less than 10%, which is the same thing as 1/10 of all the population, which in this case is all Oreos. And 30 is definitely less than 1/10 of all Oreos, right? We're talking about all the Oreos that have been created. Okay, so I'm gonna kind of write out my explanation of that 10% condition again. We're using this since we are sampling without replacement. And again, that is generally the case. You will always have to check this 10% condition. Okay, so then it says in the formula for the standard deviation of the sampling distribution of X bar, we don't actually know the value of sigma. If we knew sigma, the population standard deviation, we would know mu, because mu is part of calculating the standard deviation. The mean is part of calculating that. And we're trying to estimate mu, which means we don't know mu, and therefore we don't know sigma. So we're going to use S sub x, the sample standard deviation, instead. And of course, instead of calling it standard deviation, then we call it the standard error when we substitute that sample standard deviation in for the population standard deviation. Okay, so standard error is S sub e, but this time it's sub x bar instead of p hat. And this is equal to that S sub x divided by the square root of n, which so far in these notes I've been using S sub x. I interchange S sub x and s. They are literally the same thing. So again, S sub x is equal to s. We use both. Okay, so let's look back up to the problem. S sub x was 0.0817 grams, and then n is 30. That's the sample size. So let's plug those in. 0.0817 divided by the square root of 30. All right, I'm going to go ahead and type that in my calculator just to give you an idea of what that number is. But when we use this later, we will rewrite this whole thing so that we don't end up with rounding error. Okay, so 0.0817 divided by second square root of 30. Okay, so I got 0.0149. 4 decimal places is probably fine since that's what my standard deviation was given in. Okay, so it is 0.0149. All right, so the next question says, would it be appropriate to use a normal distribution to model the sampling distribution of X bar? And again, this should make us think back to that section 6.5 where we talked about the central limit theorem. And if you remember, the condition for the central limit theorem to be met was that either the population distribution was normal, which we don't know anything about this population distribution, or the sample size is large enough. And that boundary was greater than or equal to 30. So yes, our sample size is 30, which is greater than or equal to 30. So by the central limit theorem, CLT for central limit theorem, it would be appropriate to use a normal model. Okay, that's good news. However, whenever we're finding the margin of error for a confidence interval for a proportion, remember, for a proportion, we would use Z star being that critical value based on the sampling distribution of p hat of sample proportions. But for means, this changes a little bit. We're going to use something called T star as the critical value, and this is from the student t-distribution. Your book explains exactly why it's called this student t-distribution. I'm not going to get into all of that, but sometimes you'll see it called student t-distribution, sometimes just t-distribution. Oops. Okay, so this t-distribution depends on a couple of things. Let's go ahead and sketch a normal curve. Just going to sketch one real quick here. Okay, so let's say what I wrote in pencil is a normal curve. The t-distribution depends on your sample size and what confidence level you want, which we'll discuss on the next page, but they are typically just a little bit wider and flatter than the normal curve. So they'll either look something like that, or they could be even a little bit flatter. Okay, so a little bit flatter, a little bit wider means we have more areas in the tails. And the reason for this is that we are using this standard error formula to estimate the sampling distribution standard deviation because we don't know sigma again. So I'm gonna write that down. Since sigma is unknown and we estimate it with S, okay? When we do that, when we estimate with S, that introduces even more variation or variability. And so our normal curve becomes less normal, or sorry, I should say our distribution becomes less normal and fits this t-distribution. But the larger the sample size, the closer it gets to normal, which is good for us. So we have a new table to introduce, and actually I am going to do that in the next video for the next set of questions.